We've talked about potential energy in the first year of physics. Potential energy is sometimes written as U, and it's defined as stored energy. Types of potential energy that we could consider: gravitational potential energy, that's the energy you have from raising an object to a higher point. So an object that's higher up has a higher gravitational potential energy. So this object, let's say this is the ground, this object has a smaller gravitational potential energy than this one, which has a greater gravitational potential energy. We also have spring potential energy. This is when you push a spring together, it has stored energy by being compressed. So an object with pushed into a spring, we have more spring potential energy in this compressed spring. And finally, what we're going to talk about today is electrical potential energy. This is the stored energy that we have that has to do with electric charge and electric forces. So since potential energy is stored energy, we're going to look at the charge's potential energy that has to do with the work it takes to move it to a new point. And the work energy theorem from Physics 1 says that change in energy is equal to the work done. So the work done equals the change in the energy. We're going to consider this charge at point A and this group of charges over here. So if I push the charge to point B, or I push the charge to point C, I'm going to have to do some work. If I do a work of 4 microjoules to get to point B, then I now have a new potential energy at point B of 4 microjoules. If I do 6 microjoules of work to get to point C, I now have potential energy at point C of 6 microjoules. This is stored energy. This is the energy that I have to do to get a positive charge near other positive charges. And you can see that potential energy if you let go of the charge. It's stored now, but if you let go, it'll move away in the form of kinetic energy. The equation we have for stored energy for electrical potential energy is K Q1 Q2 over R. In addition to electric potential energy, we also consider electric potential. And electric potential is electric potential energy per unit charge. So we said that our electric potential energy is defined by this. But if we want to see it per unit charge, we're going to divide it by one of the charges. That would be the charge that you're pushing, your probe charge. And you'll get that the electric potential is equal to UE over Q, or electric potential equals KQ over R. Now the units for electric potential energy, just like any energy measurement, are going to be in joules. Charge is in coulombs, and the potential is measured in volts. As the electric potential increases, the electric potential energy increases at the same rate. They are directly proportional. Electric potential, because we've divided it by the probe charge, it's independent of the charge that you're using to find it. So remember, potential is the electric potential energy divided by charge. So let's look at the example from before. We know the electric potential here, but we also know the charge we used was 10 nanocoulombs. So that means the potential at point B is equal to the 4 microjoules divided by the 10 nanocoulombs, and that gives us an electric potential at point B of 400 joules per coulomb. Likewise, at point C, 6 microjoules divided by 10 nanocoulombs is 600 joules per coulomb. So this is a picture that shows just the electric potential at these points. These points have electric potential that is independent of the charge that we are using to find the potential. So the V values are the same for any probe charge Q. The units of our electrical potential, since it is electric potential energy divided by charge, the units are joules per coulomb. 1 joule per coulomb is equal to 1 volt, which we write as 1 V. Now be careful, because now we have V representing potential, which is a variable. V is representing volts, which are units, and V sometimes represents volume, although we don't usually mix volume with potential without clarifying the difference. So just pay attention when you're using V as to whether it's a unit or a variable. Electrical potential is a scalar. It's not a vector. It doesn't have a direction, it just has a magnitude. So we could figure out electric potential around a point. Let's say this is a charge here. And what you'll see is a pattern that electric potential will follow a certain pattern of symmetry around a point charge. So electric potential lines at the same radius from a point charge have the same electric potential. So 20 volts at this point is the same as this point and this point and this point. Those lines are called this line is an equipotential line. It means equal potential at any point on that line. Now we also have electric fields, and they're going away from the source charge as vectors. So electric field lines are always perpendicular to the equipotential lines. You can see this is the equipotential line, and the electric field line is perpendicular to it. Both the electric potential and the electric fields are present at all points in space. We just only show a couple so that we can have an idea. But there is electric potential here and an electric field here. Any point that's not marked still has potential and electric fields. So just to kind of do a comparison of electric potential and electric fields in a little more detail, electric potential tells us how source charges would provide a probe charge with potential energy. So the potential here is 10 volts, and that would tell us how much potential energy we could have at that point from a source charge, and this is the equation for it. We also have electric fields at that point, and that electric field will tell us how source charges would exert a force on a probe charge. And that's the equation. So they're similar. One is a vector. One electric field is a vector, electric potential is a scalar. An electric field is divided by r squared. Electric potential is just divided by r. Electric field points, if you'll notice, they go in the direction of decreasing potential. So we start at 10 volts and the electric field points this way. It's going to go towards 0 volts. Now let's consider the work it takes to move a charge at a constant speed from some distance delta r that is going against an electric field. So the work is going to be the change in energy, and the energy is equal to the charge times the change in potential. That means that the work, which we also say work is equal to force times distance, so force times change in r, and that's from the first year of physics, that is equal to charge times electric field times delta r. This is the same as delta V, so we just replace this part of the equation with E delta R. The magnitude of an electric field equals the change in potential, so we can over the distance. So from here to here, the magnitude of the electric field, and that's going to be at the point right in the middle, is equal to the change in potential from here to here over the change in distance. This equation gives the magnitude of the electric field halfway between the two potential points. The units for electric field are newtons per coulomb, but now that we're also using potential, we can also write them as volts per meter. So let's do one problem. Looking at this charge, 1 nanocoulomb and points A and B, what is the potential at points A and B? And to find the potential, we're going to use K times Q over R. And we get the potential at point A is 900 volts. The potential at point B is K times Q over R, and we get 300 volts. So what is the potential energy of a proton at A and B? The definition on the equation sheet is the change in potential energy equals the charge times the change in potential. But if we're not looking at a change, we're just looking at what is the potential energy. We can write it as potential energy equals charge times potential. So we'll do that to find the potential energy at A and B. It's charge times the potential at A, and that gives us this value for the potential energy at A. And it's charge times the potential at B, which gives us this value for the potential energy at B. So I just want to run through the equations we've done. There's a lot of overlap in these equations. They're very similar to each other. We started with the force equation from Coulomb's law, and that then we came up with the electric field equation. The electric field equation being the force per unit charge. Once we have the electric field equation, we can get to the potential equation because the electric field is equal to the potential divided by the distance. And we also have the electric potential energy, and the electric potential energy is equal to the charge times the electric potential.